Hey everyone, let's go and learn why I made these videos. Let's jump right in. Buckle up for part 3 of our computational fluid dynamics series. My name is David and I'll be explaining you airflow and design configurations behind the scenes presented in my previous videos. You may ask why I made these videos. Educational purpose. As I noticed the challenge comes with visualizing airflow patterns at design meetings by engineers, architects and users. There are influencing factors of how the airflow pattern is affected by furniture arrangement, laboratory equipment placement, exhaust requirements, air intake and outlet locations. Example in a GMP cleanroom standards for ISO 8 and above, low return air outlets are critical to vent out the room and meet particle count requirements. There is a risk of poor air outlet placements that may contribute to pockets of stagnant airflow which may cause particles, dust, or biological agents building up. Classic design meetings, a struggle fighting for the same space and decide who takes precedence, whose system is more critical than the others. So I decided to create CFD simulations that can provide clear, visual airflow representations to address planning challenges. Let's take a closer look at the design. This example is a single cleanroom, where key components are cleanroom ceiling that splits the space into two, ceiling space above, cleanroom space below. Now let's see what else we got here. Ventilation ducts located in the ceiling space, supply duct in blue, exhaust ducts in red, filter fan unit, return air boxes. These return air boxes located at each corner of the cleanroom. You may ask, what's the purpose of these return air boxes? It's to connect ceiling space and cleanroom space. These are basically air ducts with low air intake openings. You see, in preparation for the CFD modeling, I left the ceiling connection open. Furthermore, I created return air openings as a physical object with louvers and space between the blades to simulate air resistance correctly as real-world scenario. I'd like to grab the opportunity and say special thanks to Autodesk for supporting me doing my airflow studies. That said, let's have a look at the airflow configurations and airflow metrics. This geometry has been modeled in Revit to export into Autodesk CFD. So let's have a look at this geometry in Autodesk CFD. Now we are in CFD and we're looking at the same geometry. All geometries have been assigned to materials and the analysis have been done. There has been 400 iterations. I'm going to hide this to see the image larger and to check the airflow metrics. So to have better visibility, I'm going to hide the outer shell. Okay, we're still seeing this bluish image. This is basically the void that has automatically, every void in Autodesk CFD gets filled up and then later have to be assigned to material or medium. In this case, of course, this has been assigned to air. Here we see the material being fluid air. Okay, I'm going to hide the air as well to have better visibility. There we go. Okay, so now we can recognize the similar geometry that left over, and we can see the return air boxes, how they connect to the ceiling space from below. We can see the return air inlet. We can notice the filter fan unit, and we can notice the air ducts in the ceiling. So the airflow configuration in CFD is done in the boundary conditions, and here we go. So we see the boundary conditions. So we have 6,000 air being exhausted through the exhaust ducts from this space. So how do I arrive to the 6,000 cmh? There are 5 humid cupboards, 1, 2, 3, 4 and 5 humid cupboards in the background. Each humid cupboard is exhausting 1200 cmh. The 1200 cmh is derived at the 50 centimeter sash position. Generally, any fume hood cupboards with the width of 1500, this fume hood is a 1500 millimeter width fume hood cupboard, and at the sash height of 50 centimeter, it exhausts an average brand-dependent 1200 cmh. So 1200 times 5 corresponds to 6000 cmh. And this is how the 6000 cmh is being exhausted here. And there is a plane here in red that's been specifically assigned to be a fan that is exhausting 6000 cmh. And this simulates the exhaust fan. If we are exhausting 6000 cmh, we also do need to bring air in and make up the lost 6000 cmh. And that one is through the makeup air duct. And to simulate the air handling units that's bringing the makeup air in, there's a plane here shown in red and assigned 6000 cmh. You see the airflow direction as well. So now we have 6000 leaving the room and 6000 coming in. So 6000 comes and flows into the clean room plenum. Then we have 12 filter fan units. These are the filter fan units here. 12 filter fan units have been calculated that the corresponding airflow is enough to meet ISO 7 cleanroom grade. Let's have a look at the filter fan units. Okay, these are the filter fan units conditions. So we see here in purple color, and this plane specifically has been modeled to have this geometry. So I can assign it to be a fan, and this geometry has been assigned as a fan, and each of these fan corresponds to 1000 cmh. So 12 filter fan units and 12 times 1000 cmh is 12,000 cmh. And that's the only conditions that have been set up in this CFD. We have 6000 leaving the room, 6000 coming in, and we are moving 12,000 cmh from the plenum down to the clean room. So 6000 gets exhausted and 6000 gets recirculated. As we move 12,000 down, 6000 goes into the fume hood cupboards and 6000 gets recirculated back through the return air plenum. And this is the CFD analysis that we want to see if it's functioning well. So let's move into the CFD results. So at the moment, there are no traces set up. So we can set up traces at wherever we want in this study. So let's say that we wanted to study the airflow patterns right below the filter fan units. So here we see the top view and we see 12 filter fan units. So if I were to set up the traces and the checked area, say we wanted to check the area just below the filter fan units to see how the airflow patterns behave and whether it meets GMP cleanroom requirement. I'm going to check a front view or side view. I need to move this plane of traces into the checked area. Okay. So I'm going to grab it. I'm moving it through the ceiling plenum, and we want to check just below the filter fan units and to check how the airflow patterns are behaving. So I'm going to drop it just right here. It's going to take several minutes for Autodesk CFD to calculate it. So we are going to be back when this is done. Okay, we are back and the calculation is done. This has been several minutes, for you just a blink of an eye. So we can see the calculation has been performed, and this may look overwhelming and also it may look very nerdy, but we can see the airflow patterns, how they're flowing through the entire clean room. So if we're just focusing on this fume hood cupboard, and we are looking at this fume hood cupboard from behind, and we can see that the patterns, the splines are converging into the exhaust duct, and then they're going through and going out through the exhaust duct. We can also see how the airflow, the splines being pushed down from the filter fan units, and some of them flows into the fume hood cupboard and some of them flows into the return air boxes and then flowing back to the ceiling. Same on the other side. these splines are flowing into the return box and flowing back to the ceiling plenum, and then arriving to the filter fan unit and being pushed down to the cleanroom space. This perfectly shows it's an excellent CFD analysis showing that this cleanroom meets GMP requirement. Every single corner and part of the room has been vented out. There's no dead zone left out not being vented. So this could look overwhelming and hard to understand for some people, and this is why I created a virtual airflow analysis in Autodesk CFD, in Autodesk 3ds Max that I'm going to show you later. But also the number of splines are so overwhelming that we can just pick lesser splines. We can specifically pick if you wanted to do just a return air box. And in some of the previous videos, I only showed the supply air duct, which is way lesser number of splines and easier to understand. So that said, let's remove this. And I'm going to show you the traces that was set up only for the specific analysis at the outdoor air duct. So this is the outdoor air duct. And let's set up the traces only for the outdoor air duct. So I'm going to move into a right side view. There we go. This is the outdoor air duct. I'm going to set up the traces here inside duct because I wanted to specifically analyze the airflow flowing through the air duct and flowing out of the air duct and show how it's flowing through the entire clean room. Now this traces back to side view. Okay, here are the plane of traces. So for the study, I have to move into where we want to analyze. So that point, the data cloud is inside within where the airflow is. There's nothing going to be shown here outside of the clean room, so I have to move it inside where the CFD analysis have been done. So, and I specifically want to analyze inside this duct. I can drop it anywhere in this duct. The reason I prefer to drop it as close as possible to the fan, so I can see the laminar airflow in this duct and I can see how the air is flowing out of this duct. So I'm dropping it here. This calculation was way faster because the analyzed area is significantly lesser than the previous one. So we can observe the laminar flow from these traces point. These splines, the airflow pattern is laminar throughout the entire duct, and we can see how it's flowing out and turning back from the cleanroom plenum, then moving down to the filter fan units, and the filter fan units pushing it down, moving it into the cleanroom, and we see the spline here, this specific one, moving into the fume hood cupboard, and from the cupboard is moving out through the exhaust branch duct and moving into the exhaust duct and leaving the space. Some other splines are moving into the return air box and moving back to the ceiling plenum. Same as on the other side. So now it's easier to see because we're analyzing lesser splines, depending on what we want to analyze. We can have a look at it a isometric view. This is how the isometric view is looking like. So this is where the traces have been set. We can see the laminar airflow, we can observe it and flowing into it. So this might be easier to understand due to lesser splines, but it may still look nerdy. And so the reason I set up the virtual airflow and also doing it in 3ds Max, because I can do a virtual walkthrough while studying the airflow patterns. And we can animate it, we can represent the direction the pattern is flowing. Because some people may question that how do we know that this spline here is flowing upwards or flowing backwards. So to do that, we move into Autodesk 3ds Max. So this calculation, this simulation that has been done, and there has been 400 iterations done. You can set different number of iterations if you like to be more accurate. I'm gonna hide this. This point cloud was exported into 3ds Max. So now we are in 3ds Max, and you see the same geometry as you observed before. And that point cloud is this. This is the point cloud that came in from CFD. That's a large number of data and calculation that was done. So the splines that we are seeing, if I'm going to hide this point cloud, the splines we are seeing here is not a random splines that I created. This is based on the calculation that we imported in. And these splines I specifically picked. I'm going to hide this outdoor air duct because I wanted to pick up the same exact points. We can pick up any points within this cloud, but I picked up 8 splines only. These 8 splines, 4 and 8. And it's only 8 splines that we are analyzing through where they flow within this clean room. We can pick up 12, we can pick up way more numbers. The larger number of splines we want to pick up, the longer the calculation it takes. And it may become impossible for a 3ds Max to calculate through, or my computer is not strong enough to calculate it through. So we can be mindful how many splines we want to analyze. So I picked up 8, and this is where you see it, and we can animate it. So you see the raw data, and this is how the animation has been done. You can observe how the air patterns is flowing in the outdoor duct, laminar flow. If I'm showing the outdoor duct, that's where it is, and you see where it's flowing out of the outdoor duct. We can spin this around. There it is. And we can also observe how it's flowing back from the return air plenum right here. So you see it's flowing back. I can hide the outdoor air duct again, and there they are flying. You notice that some of the other splines also flowing through this return air plenum. And this is only the 8 points. We can pick up any points within this entire clean room, and we can analyze them where they are flowing. So this is how the virtual 3D animations have been done. And this is how 360 images have been taken inside the clean room. And I was able to do the virtual walkthrough. For example, the one that you can access through the several portals. For example, do feel free to check out the A to the X site, and you can click on this cool post. And if you get to this post, you're going to see this virtual walkthrough. And these are the airflow patterns exactly you see and you saw just in 3ds Max just now. Feel free to spin around. This was created from using 3ds Max. If you made this far in the video, thank you for your time and thank you for your interest. If you like the content, please give a thumbs up. It will help to spread the knowledge. Don't forget to drink some water and have a great day ahead. Peace out.